Okay, so at this point, we've looked at all the different tricks to find derivatives, all the different rules. We've looked at the definitions of the derivative. We have looked at applications of derivatives like optimization and things like that. Now we want to do something else, and I'm going to kind of be honest here right at the start, especially because I know most of you are engineering majors here. This is another one of those weird little math things, like with the whole epsilon delta definition of limits that we did, that kind of explain why the math we do works. So it's going to be a little bit math heavy with a lot of terminology and notation and stuff. Don't get lost in it. When we get to the end, the idea and the principle will be really straightforward, notationally speaking, but because your book mentions it, I do want to kind of go through all of the math the way your book does, just so that when you're reading it, you have an understanding of what your book is saying. But the principle, the idea, is similar to the epsilon delta proof of a limit. It's that kind of thing. So we mentioned the definition of the derivative, and we know there's different ways to write the limit definition. This is the one we're going to use for this because it's the one your book uses. F prime of c is equal to limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. So standard definition right there. But now we're going to manipulate this a little bit. I'm going to set this equal to 0. And what I mean is I'm going to subtract f prime of c over to the right. So now this is equal to 0. But now I want to write this as one continuous fraction, so I'm going to multiply delta x on top and bottom here, just so I can write this as one fraction. And I get 0 equals the limit as delta x approaches 0 of f of c plus delta x minus f of c minus f prime of c times delta x all over delta x. And again, if you're actually wondering as we go through this, yeah, this is actually what mathy type people tend to do. We just kind of take random math stuff and manipulate it and mess around with it and say, hey, what comes out of that? And then random stuff pops out and we're like, cool, look what I did. So I'm not sure if you engineering students do that. So now we have this right here. And one thing to notice is, I have a delta x here and here and here. And all things being equal, I can really treat this limit as a function of delta x, which is what I'm going to do. And I'm going to give it the notation, this right here is equal to epsilon of delta x. And again, here's where I mentioned that is not the epsilon we've been using. It's a variable. It should, in your head, kind of make you think about epsilon, in this case, error, difference, something like that. But this is not a product. This is function notation, just like f of x. It's epsilon of delta x. I'm just defining this big, huge function as a function of delta x, which I'm completely fine in doing. Good. Now, okay, one thing to note, when I talk about a derivative, maybe down here, we'll say f prime of c. Another way to define f prime of c, like to simplify this definition easier, is to use the more simple delta y over delta x. And then, of course, in this notation, the delta y on top is just equal to f of c plus delta x minus f of c. So again, I'm using different notations of the derivative in different ways we've written it. Don't get lost and confused. This delta y is just the change in y, which is the value on top there. And yes, I have to keep referring to my notes because I want to make sure I'm using all the same notation that your book does to hopefully alleviate your confusion as you read through it. Okay. But now we can say delta y is equal to f prime of c plus epsilon times delta x. And one thing I would point out right here, keep in mind this epsilon right here is really this function epsilon delta x. Your book is writing it in this notation. Honestly, I don't know why. I think it makes it look more confusing because they define epsilon of delta x as a function, and then down here you see epsilon delta x and your brain immediately says, oh, it means that. No. This epsilon, in the same way that we say f of x, and then sometimes we just say f, this epsilon is representing this function. So I could plug this whole function here in for that epsilon, and then multiply by delta x, and multiply f prime of c by delta x, and that would all equal delta y. You can actually do the algebra out. I'm not going to do it right here. I did it and then erased all the algebra before I made the video. But if you think about it, this whole thing right here, this limit, is approaching 0, which means in this notation right here, this part right here is essentially 0. In your head, think about that as 0, so it doesn't matter. F prime of c, by definition, is that up there. It's delta y over delta x. If I then multiply that by delta x, those cancel, and I'm left with delta y right here. So that's all that's really saying. It's not really explained clearly in your book, but that's all this is really saying right here. But again, the one caveat is that the limit as delta x approaches 0 of this part, epsilon, we'll go with epsilon delta x is equal to 0. But again, I stress, this epsilon is a function, that function, epsilon delta x, is a product. It's the product of this function times delta x. Don't get them confused as you read. We're going to go through a few problems once we define all this. It's probably going to have to be on another video because this explanation takes a while. But we'll go through a few problems so it's clear what's going on here. Just kind of bear with me for now. Okay, good. Now let's see. Suppose we have this. One downside, I'm out of room. All of you have access to your book and notes, so you can just look back if necessary. So, suppose we have f of x equals x squared. Now, I know f prime of x is equal to 2x. I want to find delta y, which I just defined as f of x plus delta x minus f of x. When we use the actual definition before, we use c, because we were talking about the derivative at a point. This is just the general delta y for any x right there. Well, okay, good. Then plug that in up there. We should get delta y is equal to f of x plus delta x. That's x. So that's x plus delta x squared minus x squared, which is x squared plus 2x delta x plus delta x squared minus x squared equals the x squareds cancel. I get 2x delta x plus delta x squared. Now, using the notation that hopefully you wrote down before I erased it, we said delta y is equal to f prime of x, again, replacing c's with x's here, plus the function epsilon times delta x, which then if I distribute becomes f prime of x delta x plus epsilon delta x. Again, the product of the function times delta x. Now if I kind of equate these, f prime of x is 2x. So there's my f prime of x. There's my delta x right here. So this part is right there. Then this part has to be delta x. So this is part of the definition of delta y. So this right here is my epsilon, my function epsilon, which is my error right there. In your book's notation up here, this part right here is called the principal part of the delta y, the principal part of the change of the derivative. This is called the error part. And here, the error for this one is delta x. And I will stress now, maybe the question becomes, good, well, what in the world does that actually mean? Essentially what it means is, if you are taking the derivative and you want to approximate it this way, you want to know how well the change, say the change as you go from 4 to 5 or 8 to 9, how well the derivative you get, the change you get, how exact it is. And what this is saying is, this delta x, for any problem, which we will do on another video, you will know what delta x is, your change. And in this case, that's how much your error will be, just the change. We're going to do one more here really quickly so we can see this worked out with a little bit more cumbersome problem and then go from there. So, suppose we use f of x equals x cubed, f prime of x is equal to 3x squared. Now I want to find delta y, which is equal to f of x plus delta x minus f of x, which gives me x plus delta x cubed minus x cubed. Here, I am going to just write out the expansion of that. If you cube it all out, it's equal to x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed, and I'm going to put that in parentheses so we don't get confused, minus the x cubed right here. So this is the actual expansion of the cubic if you expand it out. If I then simplify, the x cubes cancel, and I get 3x squared delta x plus 3x delta x squared plus delta x cubed. Now again, we want to compare this to delta y, which is equal to f prime of x plus epsilon delta x, which is f prime of x delta x plus epsilon delta x. I have a minute and a half, should be able to do this. But again, I see right here, there's my f prime of x delta x. So I've got that part accounted for. Here, I can factor out a delta x, and I get 3x delta x plus delta x squared delta x. Now, for the purposes of this is my delta x, my definition right here. So my epsilon function, my error, is all of this right here. I am aware this is a little bit cumbersome. We're already 15 minutes in, and all we've really done is a definition and a couple of algebraic type examples. In the next video, we're going to delve into this a little bit more and look at some more example problems to give you a better idea of what's going on. I do stress, just like with limits and the epsilon delta definitions before, right now we're kind of deliberately working through the machinery of this so you can see the math going on. Ultimately, just like with derivatives, once we understand the machinery a little bit and we mess around with it a little bit, we'll have shortcuts that allow us to solve these problems a whole lot better. So just kind of bear with this for right now. There is a meaning at the end.